Okay, this is the second example of using Mathcad to do singularity functions, so I don't really need to say anything about this one. I talked about that in the previous video. It's simply all of the singularity functions wrapped into one function name called singf. I pass it the power of the singularity function, I pass it the a constant of the singularity function, then I give it an x at which to evaluate the singularity function. This one I'm looking at the geometry from our Shigley textbook in the appendix 9, sample number 6, which is a simply supported beam that has a point load which is not located in the center of the beam. It's a distance a from the left hand end, difference b from the right hand end, and a plus p is the overall length of the beam. And so I'm going to use numbers for this example. I have to use numbers if I'm going to be using Mathcad. I can't do algebra or symbolics if I'm going to be using Mathcad. And so I'm going to just assign a value of 1,000 to the load. A is 16, L is 18, B is L minus A, which is 2. So in this case, my load is very, very close to the right-hand side of the beam. That's just how I chose the numbers. And my reactions in this one, let's see, I already went through the reactions, and I did this one as a singularity function purely by hand. And we did the statics and saw our reaction functions. And so it should be that our total reactions should equal that total load of 1,000 pounds, and they do. And so now I form my load singularity function. And I'll have three load terms, the R1, the F, and the R2. And since they're all point loads, and the point loads use a -1 flavor of the singularity function, so my Q of x is R1, the value of reaction 1, times singularity function of the -1 power, starting at x equals 0. Then F is a singularity function of the -1 power as well, but it's got a negative value because it's pointing down. And it starts at point A, not at x equals 0, it starts at x equals A. Then finally I have my right-hand reaction. It's also a singularity function of the -1 flavor, but it starts at x equals L, which is out at the end of the beam. And so if I were to plot these, what I should see, and I think I've chopped my plot off a little bit, I see my left-hand reaction, which is 111, heading up. Then I have nothing until I reach out here at 16. This should drop down 1,000, and then this one should go up almost 900. So a point load, a point load, and a point load showing up when I graph Q of x as a function of x. I probably should have changed my scale though. Let's let this thing go down to a -1,000. Okay, small load, very large downward load, and slightly smaller upward load. Now I take my Q function, copy it, I paste it right here, I change the Q into a V, and I change all of these -1s into zeros. That's all I do. And then I can plot my shear diagram, which goes up and holds constant, and then it drops down by 1,000 and holds constant, and it jumps up to close. And the fact that my shear starts at 0 and ends at 0, which is appropriate for this beam, is only true because I have the right values for R1 and for R2. There's my shear diagram drawn for me automatically, and I get these steps in it because of the singularity functions. Now I copy and paste it right here, and I change V into M, a trivial edit. I change my 0 here into a 1, I change that 0 into a 1, and I change that 0 into 1. Pretty simple, right? Copy and paste, and change 4 things. And plot it. And here's my moment diagram, and my moment is 0 at the left-hand end. My moment goes higher and higher and higher and higher. That beam is smiling. And then finally, when I approach my point load, I head back down with the moment, and it closes back to 0, again because I've got the statics done. Now what I need to do is the next integration. So I copy and paste, and I change M to EI theta, and I promote all of my 1s in the first spot to 2s. But now that I've gotten this far in the integration, I also need to divide by 2. And I brought in a C1 value. For now, I'm going to presume C1 is 0. and let's plot the slope function. And what I have with the slope function is 0 at the beginning and a positive slope at the end, and that is not true, but it's because I don't have the right value of C1 yet. Then I copy and paste it right here, change EI theta into EI y, change all of my 2's to 3's, a 3, a 3, a 3. But when I go to a power of 3, I have to divide by 3, but there was already a 2 there, so 2 times 3 is 6, 6, and 6. So I had to change 7 trivial things to change there, change the 3's, and change the 2's into 6's. I did go from C1 to C1x, and then I brought in a new constant of integration C2. And for now, I'm going to set C2 equal to 0. That may be right, may be wrong, we'll see. But I can plot EIY now, and what I have is 0 deflection at the left-hand end and substantial deflection at the right-hand end. And I know that's not true because I should get 0 deflection at both, but I haven't dealt with my boundary conditions yet, or my constants of integration. So now I'll deal with the constant of integration, and I know that at x equals 0, EIY should equal to 0. And so 0 on the left-hand side of my deflection equation, copy, paste, and change all of my x's to 0. Change this x to a 0, that x becomes a 0, that x becomes a 0, and that x becomes a 0. When I do that, everything goes to 0. The only thing left is C2. And when I ask Mathcad to find C2 for me, it finds a 0. So C2 is equal to 0. That's the easy one. Then at x equal L, which is 18 in this problem, then my deflection is also 0. So I take my deflection equation and I put a 0 here, and I change all my x's into L's, capital L's. So I put a 0 here, all my x's become capital L's, including this one, and I have my C2 constant. It is 0, so I'm just going to leave it there. And I ask Mathcad to then search for the value of C1, which causes this equation to become true. And it finds a minus 5.926 times 10 cubed. That is apparently the value of C1. When I rewrite my EIY equation with the new values of C1 and C2, and I plot my EIY equation, it looks like this, and notice my deflection to the left has gone to 0, and my deflection to the right has gone to 0. And the red curve is my solution using Mathcad Singularity Functions. The dots is the author solution, and if you go into the appendix, you'll see that there are 2 different expressions for the deflection. One is the deflection when x is less than a, and this was the equation that was in the book. And then when x is greater than or equal to a, this was the deflection equation. So I've implemented both of them in Mathcad with an if statement. So this EIYA, A stands for author solution. So the author's EIY function plotted has some if statements in it, and it plots right on top of the Mathcad solution. So I am confident that I've got a good Mathcad solution out of this thing. That ends this video, and so I'll see you on Friday. Enjoy.